Hello, my name is Markus Tempelmayr. I am a PhD student at the Max Planck Institute for Mathematics in the Sciences. And in this short video, I want to present a recent preprint on a diagram-free approach to the stochastic estimates in regularity structures, which is joint work with Pablo Linares, my supervisor Felix Otto, and Pavlos Tsatsoulis. We consider a quasi-linear parabolic SPDE, where you should think of 2 as being the time direction and 1 as being the space direction. And on the right hand side you see a nonlinearity A that you can assume to be as smooth and elliptic as you want, and a random driver psi, of which for the moment we just think of a very rough function. Then these equations are what's called singular, namely if you assume for the moment that psi has Hölder regularity alpha minus 2, then the best we can hope for the solution u is that it is of regularity alpha, and hence also a of u will be of regularity alpha. Then the second derivative of u is back in c alpha minus 2, and hence the product of a of u and the second derivative of u is only well defined if alpha is larger than 1, and for alpha less than 1 there is a problem in the equation, and it's not clear what it means for a function u to be a solution of this equation. On the other hand, the equation is what's called subcritical if the noise is not too rough, which means that as long as alpha is positive, we expect by a scaling that on small scales u looks like the solution to the linear equation. And that gives some hope to at least say something about this equation. Why should we care about this? So for typical interesting applications, one would consider thermal fluctuations, for which space-time white noise is typically considered, and in one space and one time dimension that corresponds to alpha being 1/2, which is exactly in this regime of singular but subcritical. So for these subcritical equations, in particular for semi-linear equations, the theory of regularity structures was developed by Martin Heira and co-authors, where the main idea is that you express the solution u by a generalized Taylor expansion, which means that you do an expansion not only with polynomials but also with more general objects like functions or even distributions. These objects are here denoted by pi x and typically called the model. Our goal is now to generalize from semi-linear equations to quasi-linear equations, and having at the same time a slightly different perspective on the theory. However, as for the original theory, our approach comes in 3 big steps, namely an algebraic one, where one considers the structure that is necessary to build these expansions, which is carried out in an earlier work by together with Pablo Linares and Felix Otto, and which concerns mainly Hopf algebras and their representations. Next, one has to perform a probabilistic step where one stochastically estimates these expansions, and this is the topic I want to speak about in this video. And finally, one performs an analytical step where one uses the stochastic estimates to deterministically construct a solution, and that was carried out in a work by Otto, Sauer, Smith and Weber. Now we will focus on the middle block, and to do so, to obtain some stochastic estimates, we first have to make some assumptions on the noise. So what we assume is that first of all psi is smooth. That means problems that I explained on the first slide do not come up, but at the same time we think of it as approximating a rough object, and everything we do will be completely uniform in this approximation. Moreover, we assume that the noise is stationary and reflection invariant in space, and most importantly, it satisfies a spectral gap inequality. That means that for cylindrical functions, the variance is estimated by a stochastic norm of its derivative. For example, Gaussian random variables with Cameron-Martin space H would satisfy the assumptions A2, 3 and 4, And if we mollify in addition with a smooth and reflection invariant kernel, then this noise in addition satisfies A1. Now we should have again a look at the equation, namely the problem I pointed out earlier translates in this setting to the fact that we won't be able to obtain uniform stochastic estimates, and we have to modify the equation. We do that by introducing a counter term that's here denoted by H, that is a priori allowed to depend on the nonlinearity A, on the solution U, and on the noise Xi, and of course also on the space-time point Y. But of course that's too general for a meaningful counter term. So what we do is we postulate that first of all it is local in the solution U, meaning it depends on U only through the space-time point Y. Moreover, it is deterministic, hence not explicitly depending on the realization of the noise. It only depends on the noise through the law of the noise. Next, we assume that it is shift invariant in space-time. And last, that is shift covariant, which means that given a counter term for an equation with nonlinearity A evaluated at the solution shifted by a constant, that should give the same as the counter term to a different equation, namely to the one where we replace the nonlinearity A by a shifted nonlinearity, shifted by this constant, and then evaluated at the solution. All these postulates translate in our setting to the fact that the counter term in fact is only a functional of A, and not of the plane nonlinearity A, but of the nonlinearity A shifted by the solution U itself. Let me also mention that the last two postulates here just express that the origin that we choose in Y space and in U space has no effect on the renormalization. Now is the moment to build this local expansions, the model, and our philosophy to do that is to consider first of all nonlinearities A at once, and second the whole solution manifold. And since we work with a PDE that has an infinite dimensional manifold of solutions, we think of it as being parametrized by space-time polynomials P. That way, we can interpret the solution U not only as a function of space and time, but also as a functional of the nonlinearity A and the parametrization P. And at least formally, that allows to take partial derivatives with respect to the Taylor coefficients of the coefficients AK and Pn of the nonlinearity A and the parametrization P. Namely, for a multi-index beta, we define the beta derivative in these directions and denote by pi beta the beta derivative of the solution U evaluated at A equals 0 and P equals 0. And analogous, we denote by C beta the beta derivative of the counter term H evaluated at 0. By applying this beta derivative to the equation for U, we obtain an infinite hierarchy of equations for pi beta. Namely, for example, for the multi-index 0, we obtain the linear stochastic heat equation. And in general, for a multi-index beta, we obtain a PDE for pi beta, where on the right-hand side, you see only terms that have been already calculated before. Here you can see in red the counter term, and you see that the structure we imposed on the counter term H translates here to this complicated looking counter term of linear combination of constants C. That will be actually very convenient later. Now we take this hierarchy as a motivation to define the centered model. Namely, we define a centered model pi x for a multi-index En as the monomial of degree n centered at x. And for a multi-index beta that is different from En, we define pi x beta by a PDE, namely the PDE from the previous slides, where now I denoted the right-hand side of the equation by pi x beta minus. And to get a well-defined object, we also impose some growth conditions at infinity and a vanishing condition at the point where we center x to a certain degree that depends on the multi-index beta. But in the theory of regularity structures, also what's called a structure group is necessary, and that's supposed to be provides transformation to change the centered model centered at one point x to another point y. More precisely, it contains linear maps that we call gamma star xy, such that I can express pi x beta centered at, so a model centered at one point x, as a linear combination of a model centered at a different point y. The existence of this group was established in the already earlier mentioned work together with Pablo Linares and Felix Otto. Now we have all the ingredients together to formulate our main theorem, which says that assuming all the assumptions on the noise hold that I mentioned before, then for any x there exists a centered model pi x and a renormalization c, in particular c is independent of x, such that first of all they are related as before, and in addition they satisfy this stochastic estimate. And moreover, the same holds for the structure group. So for every xy, there is an element that transforms pi x into pi y, and also this object is estimated in a stochastic norm. These norms are exactly the right estimates you need to run a deterministic solution theory. Now in the remaining minutes, I want to give you a vague idea of how the proof proceeds, and in particular I will show you how we obtain the first stochastic estimate for the model pi. Namely, instead of estimating pi, we start estimating pi minus, and we do so by using the spectral gap inequality. That translates into the fact that the stochastic norm of pi minus is estimated by the expectation of pi minus and a stochastic norm of its derivative. Now, to estimate the expectation, we are in good position because we still have the constant c at our disposal to choose, and choosing these c's will in the end fix our counter term h. Now we do that by the BPHZ-choice of renormalization, which means that we choose the constants in such a way that large space averages of the expectation of pi x beta minus vanish in the limit. And it turns out that this is exactly the right choice to obtain the corresponding estimate for the expectation. To estimate the derivative, we use duality, namely instead of working with the derivative, we work with the directional derivative in a direction delta psi. And that has the advantage that when you look at this directional derivative, that basically amounts to replacing one instance of the noise psi, which lives in C alpha minus 2, by a delta psi, which now lives in H alpha minus 1/2. And here you see that we have a gain of 3 half derivatives. And it's exactly this gain of derivatives that allows us to find a map d gamma such that the increment of the derivative of the model pi, namely here in purple, vanishes to a higher order. And this higher order vanishing together with the key identity here on the bottom of the slide makes a reconstruction argument possible. Now here I want to point out two facts about this identity, namely, first of all, on the right hand side we see a product of pi and of this increment that has a better vanishing behavior, and that means that this product on the right hand side is not singular anymore and can be estimated. On the other hand, you see that the left hand side involves a multi-index beta and the right hand side only involves pi x beta prime and the increment with a beta double prime, where beta prime and beta double prime are strictly smaller than beta, which allows for an inductive argument. Now on the last slide I want to show you how you go from these increments back to the estimate for pi that we were originally interested in. So as said before, let me start different. We want to end up with an estimate for pi x for a multi-index beta. So we fix a multi-index beta, and we assume the estimates for the model pi x and the increment of the derivative of the model for smaller indices. Then the previous identity allows us to estimate the increment of delta pi minus, and that on the one hand allows to estimate the increment of delta pi again, but now on level beta by a simple integration argument. And on the other hand, it allows to estimate delta pi minus by a boundedness of d gamma. Then together with the vanishing with the choice of constants we did earlier, the spectral gap inequality allows to estimate pi minus, and from pi minus finally we can go to pi with a Schauder type argument, and we obtained the estimate for pi with the multi-index beta. Now you can go to the next larger multi-index and proceed in a similar way. Now finally let me summarize. Probably the main difference between our approach and the original approach is that we approach the counter term top-down rather than bottom-up, which means that we first change the equation and then to this modified equation build the model. That has the advantage that we are from the very beginning guided by symmetries, and also allows to replace combinatorics by analysis. Namely, instead of looking on trees and diagrams, we take derivatives with respect to the nonlinearity and the noise. Moreover, the multi-index approach reduces the number of counterterms compared to the tree-based approach. Namely, it groups together certain trees that would have to be treated separately in the tree-based approach. Let me also mention once more that the spectral gap inequality complements very well with the BPHZ-choice of renormalization, since the spectral gap inequality estimates the quantity we are interested in up to its expectation, but the expectation is exactly taken care of by the choice of renormalization. Now, in the end, we obtain the fully automated and inductive proof in the whole subcritical regime. With that, I want to thank you very much for watching my video, and if you got interested in the details, I invite you to check out our preprint on the archive. Thank you very much.